Alright, hello everybody and welcome to another IFT 372 study session. Again, today is the Sunday session, so typically on these days I like to focus on homework questions or activity questions or basically whatever was needed for the homework due this evening, but again, these sessions are fairly open, so if you have any other questions, we can address those as needed as well. And we'll give it a couple minutes here just to have everybody show up or give time for people to trickle in, and then we'll get started properly. I will say generally if you have activity questions, those are a little bit harder for me to address than homework questions just because of how they're based around MATLAB fairly specifically, and it's hard for me to be able to answer a question without having gone through all the steps looking for a specific answer or problem. But yeah, so Stephen has questions about the activity, so yeah, let's get started with the activity. I will do my best to give answers to the activity, but sometimes it's, depending on the type of problem you're asking about, it can be tricky without going through. Some of the discussions are just better suited for discussion boards. Part 3, Section 3, so Stephen's asking, he doesn't understand why the number of process samples is only 7,500. Let's take a look. Part 3. Okay, Part 3, Section 3. Okay, so let's take a look. So if we, let's see. So the first thing to look at in this specific case is if we go back up to the first part of step 3, using the Rayleigh channel to filter a modulated signal and obtaining channel responses, impulse, etc. Let's see, where are we here? When we originally create the data, so for data in, we're calling the randi function with the input 0, 1, n, and then 1. And then at this point, when you're doing this, because we're not already defining n, we should have a preset value of n. Let me see if I can tell just from my notes what n would be at that point. I'll have to go up to some of the previous steps to find it. So at that point, n, when we call the randi function, and I had to scroll back up to step, okay, so you think it's 1, and that's where you're making your mistake. So I think if we scroll back up to step 1 of part 3, it's 30,000. So you can see that for step 1, part 3, we have the instruction part 3, step 1. We have the instruction now use this multipath channel to filter the input signal x equals randi 0, 1, n 1, where n equals 30,000. So we have n equal to 30,000 at this point. N as in Nike. Because again, if we look at step 3, part 3, we're generating data in using randi 0, 1, and 1. And like you said, we haven't changed n, and so n is still equal to 30,000 at that point, as far as I can see here, just looking over the previous steps. And if you agree with me on that, then we can believe the value 30,000 is small m in the paper, but I follow. Let me see, because all I was seeing is that if you look at, where are we? If you look at the bottom of page, let me see. Let me make sure I have the right page numbers for you to. And what page is that on? Because I might be looking at something different. That I'm not aware I'm looking at something different. Okay, so yeah, you're arguing about the variable, not necessarily the value of the variable. Okay, I got it. So, okay. So yeah, we'll agree that either whatever you want to call it, small m, n, whatever it is, that middle value m, we'll use m for your example so we're on the same page, but we'll agree that that value is 30,000. And so because that value is 30,000, what we're actually doing is we're taking that 30,000, the data set of 30,000 points of either 0 or 1, basically the random data stream of 30,000 data points, and then we're applying 16 modulation levels, where we have big M is equal to 16. And so if we're using 16 modulation levels, that means we're using 4 bits to encode the data. And so if we're using 4 bits to encode the data, that would mean that our symbols consist of 4 bits. And so if we're trying to find the rate of symbols, if we have 30,000 original data points, but we're splitting that 30,000, that set of 30,000 data points, so we have 30,000 data points, but those data points are being split into symbols of 4 bits. That's how we end up with number of samples processed 7,500. Because again, what matters is that we're using, at the beginning of step 3 of part 3, we're using 16 QAM to modulate the input data. So again, our input data is just a string of 30,000 0 or 1, 30,000 binary digits. We're using 16 QAM, which means that data has to be split into 4-bit symbols. And if we split 30,000 data points into 4-bit symbols, then we have 7,500 symbols. And that's what we're tracking when we're talking about the number of processed samples. The samples that we're processing are now 4-bit symbols, not the original 30,000 data points that we're talking about. And so that's all you really need to say for that one is, because we're using 16 QAM, our symbols are 4 bits, and we can prove that when we say if m equals 16, again 16 levels, log base 2 of 16 equals 4, and so we're using 4-bit symbols. And so our bit count is reduced by, is divided out into 4 because we're using, each symbol is now 4 bits, so we have a quarter as many bits. Alright, second question is that there are 2 that are close to resolve this. I think it has to do with sample rate. Alright, I think I'll need a little bit more explanation of what you're talking about there. The second question is that there are 2 that are close to resolve this. I think it has to do with sample rate. Oh, right below this. Okay, is it... Let me make sure we're on the same page. It's the following question. Okay, great. Wired. Oh, okay, okay. I just wasn't looking far enough ahead. Let's see. Oh, I see. Okay, it's in the italics. All right. Okay, so when you end up with your scatter plot, can you generally see the 3 paths that it's asking you to identify? Just generally, kind of looking at it. and maybe not necessarily looking at the visual scatter plot, but at least, okay, yeah, so you're on that same page. And so the big difference when you want to modify the code to resolve them, to address why the two paths are so close, if we look back at the formula or the code that we use to generate this path, where are we? Let me see, I've just got to track it down here. So the big thing is if you look, and this requires you to look at some of the syntax and understand basically how the equations or the functions work as you're using them. But if we go back to step 2 in this section, when we're first generating the 3-path channel, we have channel equals Rayleigh Chan, TS, FD, tau, and PDB. And so if we go, it says as stated earlier, so let me see if it has a definition in the reading. But generally, or for this problem, tau is the vector for the path delays in seconds. And so if we wanted to bring the paths closer or further apart, we have to change the variable of the path delays. Because if we have less path delay, then they're going to be closer together. And if we have more path delay, then they're going to be further apart. And so what matters is when we generate the channel, if we change our vectors for the path delay, or our tau, which is the third value in the Rayleigh Chan syntax, then so originally we have the 3 values for tau, and this is part of step 2. Oops, come on. For step 2, our original values for tau are 0, 1 to the -5th, and 1 to the -6th, or 1 times 10 to the -5th, rather. And so if we change those values, if we had 0, 0, 1 times 10 to the -6, then those first 2 paths are going to be the same path because they'll have the same path delay. There's technically not a different path there. And so those 2 paths would be even closer together, they'd be the same path. But if we change the values to spread it out further, so if instead we did 0, 1 times 10 to the -7th, 1 times 10 to the -9th, the paths would be further apart because there would be more delay. Or they'd still be closer together because we're still making smaller negative numbers, but okay, let's do it the other way then. So if we did 0, 1 times 10 to the -2nd, 1 times 10 to the -3rd, then the paths would be closer because again, it's a bigger number now. It's a bigger path delay. Negative powers are hard if you're not paying attention. And so yeah, that's the variable you would need to change, because if you change the path delay between the 3 paths, that's going to determine how close they are to the others. And tau is the variable that handles the path delay. If you increase the path delays between the 3 paths, so if you increase the distance between the signals, they'll be further apart. And if you reduce the path delay between each of the paths, then they'll be closer together because there's less of a difference between them. They're arriving closer to the same time as each other. And this is something, since it's just changing the variable, you can go back and plug this number or change the numbers yourself and observe how the value changes if you want more concrete proof of how that actually happens. And that'll let you verify that by changing the variable, either making it smaller or greater, you're having your intended effect. Yeah, no worries. So just addressing, and yeah, it's hard to necessarily read what these questions are asking for, so I definitely get it. The sample index. So if you increase the sample index, so this is a little tricky for me to demonstrate without having it in front of me, but basically, if you're looking at the visualization plot, so you should have, at the end of step 3, the plot with the drop-down menu that's set to impulse response, the sample index slider, and then your graph of, by default, I think it's the band-limited impulse response with magnitude and delay. And if you change the sample index, so if you just kind of page through from 7500 down, back, whatever, as you just page through it generally, all you're really noticing is that, where are we? The magnitude is basically increasing or decreasing depending on the signals that were generated. Because again, we generated random signals, right? So we don't really have any particular rhyme or reason to what's happening, but you can see that when we look at just the example image of the band-limited impulse response I have, or the sample at 7500, you have 0 is almost at magnitude 1, and you have a 1, or at 0 seconds of delay, you have magnitude 1, and at 1 second of delay, you're down to about 0.5. And so if you change the sample index, you're going to be getting different magnitudes at different delays. But that's about all that you really need to have for that question, is that it's either increasing or decreasing depending on the randomly generated signals. Because again, and this isn't going to necessarily be the same for everybody because the signals are randomly generated. It should be fairly similar. It shouldn't be too extreme in its difference. But just as you, and again, it's hard for me to do this without having the same sample index or the same plot in front of me because I can't really demonstrate what I'm talking about visually. But when you have that plot, what's the command that you need to run to get that? When you have your band-limited impulse response plot and you change the sample index, just observing how the graph changes as you slide the sample index down, as you select different samples, then you'll notice that you're having increases and decreases of magnitude at certain delays. And again, that matters based on the randomly generated signals that we created. Steven's helping me. It's the plot RAL function. Great. Yeah, okay. So this is just the index that we're sampling. Well, the sample index is basically the number that says which. The sample index is just which of the symbols we're looking at. Because remember we said there were 7,500 symbols that we identified? And so the sample index is selecting which of the 7,500 samples we're looking at. That's what the sample index is. So again, from the example diagram that I have here, when we look at the sample index of 7,500, we're saying that for the 750th, or I keep doing that, for this 7,500 symbol, we have a magnitude of 1 at 0 seconds of delay. We have a magnitude of right around 0.6 for the 1 second delay. And then we have a little tiny magnitude at 7 times 10 to the negative fifth. And so the sample index is just us selecting which of the symbols we want to look at and see the band-limited impulse response for that particular sample. The value of 0.5 seconds or 1 second is the path delay in seconds times 10 to the negative fifth. Let me see if I can yeah, you're still kind of lost with this, but you cleared it up slightly. Yeah, it would probably be clear if I was able to have the MATLAB simulation running to visually illustrate it, so I can work on that. Let me see if I can get that going. Sorry, the screen is going to go black for a second just so I'm not showing anything I shouldn't. Let me see if I can pull up MATLAB. Let me see. I'm just pulling up the VPN version of MATLAB, so it'll just be a second, hopefully. Hopefully the stream doesn't cut out while I'm doing this. I accidentally left Wi-Fi on instead of running a cable, so I'm a little concerned about the reliability of my setup right now, but we'll see. Okay. So I've got MATLAB running now. I just have to plug in the numbers to make this happen. So it'll just be a second as I plug these numbers in. And then I should be able to, from this, get a visual example so I have an illustration of what I'm talking about. And that might, hopefully that'll make it a bit clearer. And the tricky part going back and doing this is making sure that you actually run all the commands that you need to do. It's not so bad if you're going through the steps in order, but it's a little rough working backwards. Okay, I suppose at this point I can turn the stream back on. Hopefully that's visible, I'm sure it is. Alright, so now we're here. I generated the channel, but now I have to go back and store history set to 1. Alright, here we are. So, I threw this together super quick, just putting all the numbers in, so this may have some mistakes I'm not aware of yet, but it should be enough to at least illustrate the point. So, at sample index 7500, or symbol number 7500, we have a delay, at 0 seconds of delay, our magnitude of the impulse response is about 0.4. And then we have a little bit of a response at about 1 second, 1 times 10 to the negative 5th seconds, and that's it. But now as we flick through the sample, so again, we're just looking at which symbols we're looking at. Just as we're scrolling through, we can just, as we switch the sample index, our magnitude is increasing or decreasing on those given delays. And so you can see the 3 nodes are our 3 paths. And that's about the extent you need for the question. We don't really need to get into, or rather, the question is not expecting you to totally explain what the band limited impulse response is, or why we need it, or why we're at this point. The question's really only asking you, as you increase or decrease the sample index, what you observe. So it's fairly, you can take it fairly literal on its sleeve. It's just saying that as we increase and decrease the sample index, so as we're increasing here, we see the magnitude is increasing or decreasing. Because our delays aren't changing around, we're not having a different, our delay time is not changing. We're still stuck with, we have these 3 different points, 1, 2, and 3. But as our sample index is increasing or decreasing, the magnitude is what's changing. The magnitude of the band limited impulse response is changing. The delays aren't shifting around. Nothing else is happening. We're just looking at the magnitude as our sample index changes. And again, your values at 2358 may be different from my values at 2358 because of the randomly generated signals, but the concept should be the same, the general behavior. I think this is pushing my hardware to its limit here, so I'll try to keep MATLAB open for the time being if we're still talking about the activity, but hopefully the video isn't suffering, or the stream isn't suffering too much because of it. No, Steven, I think you're good. Again, nobody else has posted any questions, so feel free. This is your time to ask questions, so. We can wait a minute or two to see if, I think there's a couple people watching who haven't posted anything. YouTube says there's 4 people watching, I don't know. So, if there is somebody else here who has a question, they're welcome to post. But barring that, I'm fine answering your questions. If you're the only one who's speaking up, then you're the only one who I know is attending. One homework question on number 3. Okay. That's additional question number 3. Let's take a look. Okay, so yeah, this is a fun one because it's a lot less complicated than it looks, but it is a case of knowing how to set the problem up, like you said. All right. Alright, so for additional problem number 3, we're told that a TDMA system has a 25 megahertz bandwidth. So we'll start there. Bandwidth equals 25 megahertz. With single channels of 250 kilohertz bandwidth each. So channel bandwidth is 250 kilohertz. With each frequency channel containing 8 TDMA conversation channels. So each channel equals 8 TDMA conversations. And again, I'm just summarizing our variables here. If each user is assigned 1 transmit and 1 receive slot within each frequency channel, so user has 1 transmit plus 1 receive, so we're talking about two-way conversations. How many users can the system support? And there's 2 approaches you can take to this problem. I have the one I like to do, but then when I was talking to some people in last semester, they had the way they like to do it. So I'll cover both. They both give you the same answer, and they're pretty much the same. It just depends if you're starting at the top or the bottom. So first of all, we know that our total system bandwidth is 25 megahertz. And we know that that system is split into single channels of 250 kilohertz each. So the first thing we should do is figure out the number of frequency channels present in the system. And so we have a total bandwidth, a system bandwidth, divided by channel bandwidth. And that'll tell us how many individual frequency channels are available. So again, we have was 25 megahertz divided by 250 kilohertz. And again, this top-down method is not the way I would normally do it, or I think it's less clear how you would do it this way, but I think I'll start with this way, just because it's somewhat familiar based on what we've done before. And so this is telling us the number of frequency channels that are present in the TDMA system. And so if we actually do the numbers here, we end up with 100 frequency channels. So there are 100 individual frequency channels in this system. But then remember here that we said each of those individual frequency channels contains 8 TDMA conversation channels. So that means we have 800 TDMA conversation channels. We have 100 frequency channels, each of those containing 8 conversation channels. And those conversation channels are literally that. They're ways that you can have a conversation. So they're not receive or transmit channels. It's not a 50-50 split. They're just channels for sending information one way. And so with these 800 conversation channels, we know that each user requires 2 of them. Each user needs to be able to have 1 transmit and 1 receive. So for every user, they take up 2 of our conversation channels. And so that means if we have 800 conversation channels available, we have 800 channels available and each user takes up 2. That means we can support 400 users because we have 800 channels available for users to converse with. And each user needs 2 because they need to transmit and they need to receive. So they need 2 channels to be able to do their full communication. They need to be able to receive. They need to be able to transmit. And so that means given the system specifications, we can support 400 users. And so that's the top-down approach. I think that it makes sense. It's systematic. But the way I normally address this problem is from the bottom up. So we basically just do what we did before, but we work from the bottom up. So if each user has 2 channels, they have 1 transmit, 1 receive, and each channel has 8 TDMA conversations, that means we can support 4 users per channel. And again, that's 8 TDMA conversations divided by 2. So each frequency channel, let me specify that, that's a frequency channel. Users per frequency channel is 4. And again, each user has 1 transmit, 1 receive. Each channel has 8 conversations. So each channel can support 4 users. And then, again, like we did before, we can find the total number of channels equals system bandwidth divided by channel bandwidth. And again, we find that number to be 100. And so then, if we can support 4 users per frequency channel and we have 100 channels, number of users equals 400. And so I think that method is a little bit more, I'm not sure. They both work. It kind of depends on how you think and approach problems. I think this method's a little bit clearer because even if you don't know anything about the TDMA system, you can tell from the bottom up that each channel supports 4 users, and then you can find the total number of channels. But they're both, again, like I said, they're both the same problem and approach. It's just whether or not you start at the bottom with, whether you start with users or you start with channels. But whichever way you tackle it, that's what you're looking at. And there are a couple problems like this week that I'm sure you've noticed where they're basically just algebra word problems with a lot of terms that make you think it's more complicated than it needs to be. Especially like 3.12, there was a lot of stuff like that where you're thinking that it's harder than it is, but it's really just add up all these numbers and take the average. So, especially for this week, it's not always as complicated as it seems to be. Now for problem 2 and 5, do you have to convert EBN0 to decimal, or does this value remain in dB? Okay, it's problem 2. I assume these are the additional problems. For 2, yeah, okay, I see. So yeah, for SF divided by EBN0, EBN0 in that case has to be in decimal because you're doing division with it. So it's because you're doing decimal division, SF divided by EBN. You're doing decimal division there, and so that this is a decimal equation. And so that means, yeah, EBN0 will have to be decimal, SF will have to be decimal. And then for 5, let's double check. Yeah, same situation with there. You're still doing, because those two basically use the same equation, right? More or less. And so yeah, this is the decimal equation here because we have a division. And if it was decibel, it would be subtraction, but it's not. It's division, which means this is a decimal equation. So we have to convert our decibel values to decimal. Ashley, I worked out problem 5 with the equation that Aiden gave me about 16.49 and 16 users after rounding. Is that correct? Yeah, actually, that is correct for problem number 5. And yeah, that equation that I gave, again, I hate to just say this is the equation, do it, and then kind of just wave my hands about it. But I found that that tends to be the easiest explanation for that, short of more research. Let me check my, because again, I had a previous conversation with Dr. Helm about that equation. I just don't recall it off the top of my head. So that's the equation for 5, Stephen. Yeah, correct. That's the hand waving one that I just said. You should probably use this one, take my word for it. I'm good for it. And again, the eta or n in that equation, because it's easier to type out the n, drops to 0 because there's 0 voice activity. And so that everything after to the right of the minus sign gets dropped, gets zeroed out. Or well, one out. Wait, hold on. Now that I'm looking at that again, I want to make sure that is the right equation. For some reason, Stephen, so, okay, I thought this looked off to me. It's 1 minus n over s. Like that. And that might have been a typo when I first talked about it. So that's the equation that we want to be using for this. There you go. Yes, there you go, Stephen. So the right side, yeah, completely disappears. So it's just SF divided by EBN 0 times 1 when there's 0 voice activity detection. And like Ashley said, no worries, Ashley. Stephen and I are just making sure we're on the same page. But yeah, Ashley got the exact number that I got, and then you round down because it's a partial number of users, and you can't round up the number of users. Alright, hang on. I'm gonna... Feel free to ask any other questions. I'm just gonna see if I can pull up right now really quick the explanation of that formula. Because it's important to have it, and I remember having this discussion, and I'd like to be able to explain to you guys why we use that formula instead of just saying, use it, trust me. If it's any consolation, I don't think we need to use this formula again. I must have spoken with him in person about it because I don't seem to have an explanation in the email. Okay, well, it looks like I will have to keep up with the hand waving for now, but hopefully it's clear. At least it seems like we're all getting the same numbers when we're plugging in the formula. It's just a matter of why we need that formula, which is, some might say, the most important part, but it'll have to do for now. I'll do a little bit more research and try to make a discussion post. Alright, does anybody have any final questions they want to get out? We're about at the end of our time here, but if anybody has a last minute question that they would really like answered, then I will oblige. Oh, come on. There we go. Al's asking when the session will be available to stream. I don't. It will I can't imagine it'll take more than three or 4 hours. So it should be available by sometime this afternoon. I don't know. As soon as I finish this thing, I hit stop, and then YouTube takes over from there. But I don't know. It takes longer the longer it is. So for an hour, it would probably be a couple hours. I don't know. Yeah, it's definitely going to be at least an hour or two. I can say that. I can say that much. It'll at least be an hour. But I haven't been paying super close attention to when it finishes. I tend to just let it go. Alright, it looks like everybody's happy one way or the other. Al, if you have a question, Al, since you just showed up and made the effort to show up, if you have a question that you want addressed, I'll either let you know if we talked about it, or if we didn't, I will address it for you really quick right now. But other than that, I think we will wrap it up here. But alright, so yeah, we'll address Al's question here before we go. So 1312 part D, alright. Okay, yeah, so the table extrapolation. Yeah, so generally the way I approach 1312 part D is you do need to extrapolate from the table values because they don't give you enough detail to get what you need. Let me make sure I know what table we're dealing with. Table 13.1. So basically, the key thing to know, or at least work around for this problem, Steven says he just guessed. That may work. That might get you close. But so table 13.1 on page 428 is, like they said, it's an extrapolation of the formula on page 427. So 427 is the core formula that is responsible for the table, where you have P equals a to the n over n factorial divided by the summation, all that stuff down there. And so table 13.1 is basically they did the work for you on those numbers of n. So they did the calculations for 1, 4, 5, 10, 20, 24, etc. for each of the different grade of service values. But for us, we're looking at a grade of service, so we have P equals 0.02, and so that's the P value we're using. But then we're trying to find the number of servers. We're trying to find n. But again, the table is not complete. It doesn't cover all the values of n. And so if you want to, you can either kind of do a best guess estimate like Steven did. I'll call it an estimate. Or you can look at, depending on how much time or patience you have, you can go through and extrapolate out the missing values in the table with the full equation. So on page 427, where you have p equals, etc., you can solve that for the missing values. So for example, if we wanted to say, oh, let's try n equals 39 instead, then you can go and plug in the numbers into the long formula and calculate your value, your A value at that point. Because remember, n is the number of servers in the table, p is your grade of service, which tells you which column to look at, and then the actual number, the intersection of n and p, is A. But basically, you're just trying to find. So let me do an example of just the first value to give you an idea of what I'm talking about, if it's not clear already. So if we're looking at cell number 2, and yes, I'll ask, our P is 2. Yeah, we're assuming, or 0.02. We're told to work with a grade of service of 0.02. And so, for example, for cell number 2, I'm just going to work out the problem for cell number 2. Where are we? So for cell number 2, we have traffic of 66.7 Erlangs. And so, if we look at the table, we don't really have a good value for that. If we're looking at table 13.1 on page 428, our value would fall somewhere between n equals 70 and n equals 100. But we don't really know exactly where it would fall. It would probably be closer to 70 than 100, but that's about the extent of what we know. And so at that point, I would say, okay, it's somewhere in between 70 and 100, so that at least narrows my options down. So let's guess or attempt. It's a bit of trial and error at this point to extrapolate the values. Let's guess a value of 80 servers. So we can try that value. And then we end up with our big, and so we can plug those numbers. We now have enough to attempt the big messy formula of P equals, and I'm not going to type it out. It's a big number on page 4. It's the big formula on 472. So we have P equals, I take that back, I am going to type it out. A to the n divided by n factorial all over, and here's the fun part, summation of a to the x divided by x factorial. And so this is where we test your ability to plug numbers into a calculator. Hopefully you have a decent scientific calculator. And so if you do the summation of that, we'll get, Wolfram Alpha may or may not be able to help you here. I don't know. I know a lot of people like to use that, but I honestly just prefer using my calculator. And so let's see what I get if I just do this quickly. And again, this is just going to be fast calculator math, so I might make a mistake, but it'll give you the general idea of what we're talking about. So our guess is 80. That's 66.7 to the 80 divided by 80 factorial. I can't remember where the factorial is. There it is. Okay. And then that quantity is divided by, and there might be a resource on the internet that makes it just like a plug and go calculator for this. That would be hugely helpful, but I'm not aware of one, unfortunately. Let me actually, I've tempted myself with the possibility that that formula exists. That would be beautiful if it did, but here, let me. And I'm really just looking for this because I was having calculator overflow problems, so I was doing something wrong on my math. You could also see if there is a bigger table that includes more of the values by default. Because again, it does mention that it's fairly easy to calculate the table out, or program the table, sorry. Anyway, this is probably at the point where it's going on a bit too long for an explanation on this. But basically, one way or the other, if you try to calculate out this formula, either using Wolfram Alpha or your calculator. Again, I was having some calculator issues doing it now, but I know it's worked for me in the past, so I don't quite know what's going on with that. But you're basically filling in the rest of the information into that table that's not already there. So like I said, for example, if we're looking at the table for cell 2, we know that the capacity is 66.7, so it's got to be somewhere between, its N has to be somewhere between 70 and 100. We just have to figure out where. And so you can either, if you can find a bigger table, a pre-calculated Erlang B table, that would be great, because then you don't have to do the math yourself. Or you can use the formula that they give you and just trial and error your way to what you're looking for. Let me see, I just found a possible table here. Okay, you know what? Let me see if this is right, because I think I just found a better table. Let me see. Can you link to it, Al, somehow? Can you trick the filter to try to post a link? Or if not, I guess posting it in the discussion board. Let me see it first before you post it, just to make sure it's actually, I don't want to say a good one, but make sure it's not too confusing. You could also, if you're handy with programming, you could probably program it out yourself, but I really don't want to do that live because that's going to take too long. I found a good one that goes to 50, but that's not. I think you were looking at the same one I was looking at, Al. Anyway, again, at this point, I'm not going to dwell on this for too long. Yeah, that's kind of, this is a lot of time spent on effectively nothing, but you're given the base formula, so one way or another, you can figure out, if you can figure out some way to type that formula in that works, that's going to be the way you want to do it, or you can try to find a table that's pre-calculated. But that's the basic thought process, is you want to try to use that table in the formula to narrow down your to find the correct value of n. And I think Steven said he guessed. If he might have got close enough with an educated guess. But that's the general process. However you want to do it, I'll leave it to you to figure that part out. But that's what you're looking at. And I'm sure I've done it with a calculator before. Just sitting here now and trying to do it, I was not having luck. I'm sure I've plugged that number into a calculator, and it's worked out. So that's what you're looking at. But you're right. This is a little bit too much time spent on this. Alright, with that fiasco or complete failure, whichever way you want to call it, I think we'll wrap it up. Steven's supporting the pre-calculation theory, and yes, I would support that as well. But like I said, I think we're probably going to wrap this up for today. Again, homework's due tonight, activities due tonight, the practice midterm, or the practice final, rather, midterm's done with. Practice final is available at this point, I believe, should be. The discussion board should come up as well on the 1st, I think it was set to appear. I think that's right off the top of my head. So again, keep working on the discussion, or keep working on the practice final yourself, review the midterm, work on the practice final, and then when the discussion board's open, everybody can come together and collaborate again, and hopefully get everyone prepared for the final, because we don't have that much time left. I think we have a week and a bit, week and a half. Yeah, week and a bit. 2 weeks maybe technically, but alright, that's it for today. Thank you everybody for attending, and again, Al, this will be up as soon as it's up. It should be at some point early afternoon, I hope before late this evening, to cover what we did before you came. Al says this class is killing you softly. Some people would disagree with your softly. Alright. Thanks everybody for coming again, and keep up the good work. Alright, goodbye.